Thank you, Caroline, to give me the opportunity to introduce Professor Eric Taillard. It's both a great pleasure and a great honor for me. Just a few words about the career of Eric. Eric defends his PhD in '93 at the Swiss Federal Institute of Technology in Lausanne. And then he goes at Montreal, at the Center of Enterprise Network, Logistics and Transportation. He comes back in Switzerland at the Institute of Artificial Intelligence in Lugano. And since 1999, he's professor at the University of Applied Science of Western Switzerland. So Eric has an international reputation in the field of metaheuristics. Just a look on the list of his co-authors. You can find Glover, Laguna, Sandro, Hertz, Golden, Gambardella, Potvin, Laporte, Dorigo, Voss, Talby, Esgaun, and it's not exhaustive. Once again, it's a great pleasure for me to listen to you and to listen about metaheuristics, and I think not only but the contextual approach.
Yeah, if I have time. Okay, thank you very much for the introduction, and I would like also to thank the organizer for inviting me here in this very nice city of Troyes, and give me the opportunity to thank you for introducing metaheuristics. So, yeah, I can go there with maps. So I will speak about metaheuristic and make an introduction to metaheuristics, and here is the table of content of my talk. So I will first speak about basic block of metaheuristic, which are constructive methods. When you have succeeded to build a solution, perhaps a bad one, then you may want to improve this solution, and this can be done with a local search. And then, if you are not happy with this improved solution, then you can go with a randomized method to try to improve this solution a bit more. And next, still not happy, you can try to introduce in metaheuristic some learning principles, and we'll see how to learn to build solution or learn to improve solution. And finally, if you have a very large problem instances to solve, then you will perhaps use a decomposition method in order to optimize certain parts of your problem. So I will start with an introduction. This presentation, in fact, is that's a spam of the day. It's based on this book here that says open access. If I can. Okay, so this book is an open access one. So if you click here, you just get a PDF of the book, and if you click here, you got the Python code to the book. And there is also an archival version here of the books, but it's not a free access, except it for Caroline, who will get and to lighten the slides, since I didn't want to add 3 times on each slide This is due to Fred Glover, this is due to Max Servo, and so on. I have not put the references on the slide, but they are grouped at the end of the conference. Okay, what can be a definition of metaheuristics? This is some kind of definition. There are others. For me, metaheuristics, that's just a way to build heuristic. And such a set of building blocks for designing heuristic. And perhaps the first building block is problem modeling, but problem modeling is certainly not specific to a metaheuristic, but we have to do that whenever problem we want to solve. Generally, in metaheuristic, we are optimizing unique objectives, so we make a mono optimization. But we could model our problem perhaps differently by a classification method or by simulation, or we can also decompose our complicated problem into a series of different simpler problems to solve. Then the second building block is the solution building. And then you can try to improve a solution, building block. And at the end of this talk, we'll see how perhaps we can divide a problem into subproblem and optimize this part independently. And I've designed a special way that is called pop music. And also, if you mix exact method for subproblem optimization, this is sometimes called Metaheuristics. That is also some thing that is relatively new, but that's become important. And finally, the last building block is learning. How can we learn to build solution? And this is typically the field of artificial ants colony, or how we can improve solution with the local search. That's the idea of taboo search. And we can also try to learn with different solutions, mix them in some sense, and that's typically genetical with surface search or particle swarm. We are dealing with combinatorial optimization, and we have problems that are simple, and they are saying that they are simple if we know polynomial algorithm on classical computer for solving them. Typically, the shortest path algorithm is a simple problem, because even if we have an exponential number of ways to come to try, we were able to choose one that is efficient, and there are efficient algorithms that exist even before quantum computing that are about 100 years, 1 century, designed 1 century ago by Jarny, and reinvented later by Dijkstra, and we have other out of the manifold algorithms, for instance. And sometimes if you change just a little bit of a simple problem, then it's intractable, and it enters in the NP-hard or NP-complete class. And typically, the elementary shortest path is a difficult problem. We don't know, we have no efficient polynomial algorithm on classical computer to do that. And why is this so? Because if we take the probability salesman problem, which is known by almost everybody, where we want to find the shortest tour going through a number n of cities, even distance matrix Dij, then you can transform this problem into the elementary shortest path just by taking vertex you split this vertex into two, and then you complete this graph with all the possible edges, but an edge between S and P, and the weights of the edges are the weight of your traveling salesman problem, diminished by a large quantity. Here, the large quantity was 50. And if you are able to find the elementary shortest path, so the path that goes from S to T without passing twice by another intermediate point, then in fact you are able to find the best tool of this difficult, notoriously difficult problem that is a predictive problem. And for solving the public safety problem, what if we really want the best possible solution, we have somehow to enumerate all the solutions in extension. And so if you have here in the horizontal axis the size of the problem, and in the vertical axis time to solve it, then we see that even with relatively small problem instances, the time to do that will grow very rapidly above the expected life of our universe, which is not the case for polynomial algorithms that are here. If you have an algorithm n cubed, it will take few centuries. And if you have a search algorithm in a logarithm of n, then you can look for an entry of the entire Google database in a fraction of a second. It is very important to model the problem you face in an appropriate way. Suppose that for the next COVID, you have to find this genetic sequence here, AJATAJT. But your technology does not allow you to discover from a gene only, you can only know which are the 3 consecutive letters that appears in your genetic sequence. So if you expose your gene here to your detector, these will say you, oh, I have detected EJA, GAT, ATA, and so on. And knowing that, you want to reconstruct this genetic sequence. The natural way to do that is just to create a graph with each vertex being the 3 nucleotides that were discovered. And then, if you have discovered AGA, and if you think that maybe AGA is completed with a T after, and precisely you have detected GAT, then you put here an edge between AGA and JET. And you do that for all the 3 nucleotides that you have detected. Now, what you have to do for reconstructing this sequence is to find an Hamiltonian path, so a path that goes from through all the vertices of that graph. In fact, an edge here corresponds to 4 nucleotides that could appear in your sequence. But you can also model the problem directly on the arcs, and each arc represents 3 nucleotides that you have detected. So if you have detected AGA, you will create an edge between, in fact, 2 nucleotides, AG and GA. And now, in this graph, what you are looking for a Euclidean path, that is to say, a path using every edge once. And this problem here is simple. It can be solved in linear time, while this one is closely related to the traveling salesman problem, and that's a difficult one. And now, perhaps, with quantum computing, we'll be forced to imagine other ways to model problem instances. Okay, I will start with constructive method. I think that every students have seen once the Kruskal algorithm for finding the minimum spanning tree. So you are given networks with a set of edges E, a weight WE for each edge, and you want to have a minimum spanning tree, so a subgraph that has no sign curve and that is connected. And the Kruskal algorithm works as follows. You make a copy of all the edges in set R, that's the edges that remains for building your tree. And then, while this set R is not empty, you choose an element E prime that minimize, that have minimum weight. Then you add this edge to your tree. You remove from R all the edges that you cannot add anymore in your tree. That is the edges that would create node with degree 3, or that will create a cycle. And you repeat this again. And in Metaheuristics, we think, oh, can we reuse this for solving another type of problem? And so we have here the greedy constructive method. So instead of having a graph here, you have given a partial solution S, that is generally the empty set initially. You have a set E of elements that constitute a solution, and for each of these elements and each partial solution, you can create an incremental cost function. And then you can apply exactly the same process as before. You choose an element E prime that is optimizing your incremental cost function. You put this element in your partial solution, and you remove from R all the elements that cannot be added anymore to your partial solution. So Kruskal algorithm is so-called greedy method, where you build a solution step by step, element by element. At each step, you pick an element that looks to be the most appropriate. And when you have made a choice, you don't choose this choice. And it works for the minimum spanning tree. It's a polynomial algorithm for this simple problem. So we can try to use this for solving or getting a good solution or not too bad solution to a hard problem, for instance, for the traveling salesman problem. You start from a trivial solution, partial to containing, let us say, just a single city. And the elements that you can add to your solution is a new city. And the incremental cost function would be, for instance, the minimum detours that you need to do to insert this element, this city E, in your partial solution. And the least cost insertion heuristic for the polarization problem is just you choose a city with the lowest incremental cost. And if you apply this to this tiny problem instance here, saying, for instance, that this is your starting city, you add one city that with a smaller detour, and so on, and you have a tour that grows, and finally you end here with this solution. The problem is that you don't know, and generally this last solution is not the best one, because you have a very myopic view when you want to insert new elements in your solution. So to be less myopic, then you can make a kind of enumeration tree. But you don't want to have an exponential approach. So what you can do is that at the first level, you add here one element, and you select among all these partial solutions here, the p-best one, and then from this p-best solution, you can try to complete them again. And here you select at level 2 also p, and so on up to level k. And then at level k, there is one of these partial solutions here that is the best. Maybe that might be this one. And finally, you say, okay, I want to add definitively in my greedy algorithm this element here, because it is part of this part of the tree. Naturally, with constructive method like this, you get solutions that are very not so good. So you may want to improve this solution. So here we can see what exists as local improvement algorithm in the literature. And again, there is a local search algorithm that is a Bellman-Ford algorithm for shortest path, where in fact you start here by building a trivial solution. You just say, okay, I just go directly from my starting point S to each vertex I directly. So I have to pay the weight of the arc Si to go there, and it can be infinite if this arc doesn't exist in reality. And then you have a main loop here where you try to improve your solution. And here, how are you improving locally your solution? You pick each arc, ij, and you try to answer the question, it is better to go to j with the path that I have already found, or do I go through I just before? And if you detect that it's better to go from I to go to j, then you make a little modification in your solution. And since you may have negative circuits, you have to stop here if, in fact, you have made this loop more than the number of nodes of vertex that you have in your graph. So, in fact, the Bellman-Ford algorithm is just kind of local search. It was found for the photospace, as does the simplex algorithm for linear programming at each step. you improve a little bit your solution. And it starts with a solution that is obtained with a simple method, a fast one, and then you improve it with local modifications. If I come back to the traveling salesman problem, you can apply this very easily. Suppose that you have your tiny example here, and you have got this solution here. That is obviously not optimal because you have two edges that crosses. Then you can say, okay, maybe I can replace these two red edges that crosses by two other ones, these two dotted here, in such a way to improve my solution. And from there, I can reapply the process and try to find two other edges that can be replaced by water here. And you do that, and then you stop in that solution that looks not so bad. So this neighborhood here, because we are modifying slightly the solution, this neighborhood is sometimes called to exchange or to opt local search. So the basic principle here is just replace two edges by two other ones that are better. There are several different ways of implementing local search. Here is a frame that corresponds to the best improvement policy, where in this loop here, you are looking from all the neighborhood which is the best solution in the neighborhood. So the input of local search is solution. You should specify neighborhood that is a subset of solution for each solution that you can get by just making a small modification. And here I suppose that I have a fitness function f that I want to minimize. So here I find the best possible neighbor of my current solution S. This best neighbor is retained here. And if you see that this best neighbor is better, strictly better than the current one, then you make the modification. And you repeat that until you cannot find a better solution. You can also extend this process to multi-objective optimization, where you have also a solution, a neighborhood structure, and not only one objective, but lots of different objectives, functions. And so I noticed this with vectorial notation. And the Pareto local search algorithm works with, in fact, two procedures that are making just ping pong. The first procedure is the neighborhood evaluation. So you evaluate all the neighbor solution of your current solution S. And for all neighbor solution, you call update Pareto from your neighbor here, and you provide the value of all the objective functions. And update Pareto here will just update the Pareto set, so the set of solutions that are efficient, and that can be the ones that you have to retain. And update Pareto just got a solution with these objective values, and we'll just see whether this solution is better or dominates a solution on the approximation of the Pareto set P. If it is the case, then you remove from the Pareto set the solutions that are dominated by the new one. You include this solution in your Pareto set, and then you call neighborhood evaluation for this solution S. So you go there again, and you make a kind of ping pong. So I see that there are people that take picture from this talk. That's not very efficient. Just Google Eric Taillard. Then you will see presentation slides somewhere on this web page, and then you can download the slides.
I put a link on LinkedIn directly to the book of Eric Taillard.
Oh yeah,
Google me on LinkedIn, then you get.
Yeah, it's also direct in the slides. Okay. So you just click on the title of the conference, or no, on the slides. Okay. Thank you for the spamming. So when you apply this local search algorithm, then you generally will not get the best possible solution that is a global minimum. Because here is just an illustration. Suppose that you want to minimize a function of a discrete variable x, and that your neighborhood is just to modify by 1 unit, single unit, the value of x. Then, if you end with your local search in this solution there, then you have no neighbor solution that is better than this one. So your local search will stop here. So all these red points are local optima. The blue one is the global minimum that is the graph, that's the ones that we want to identify. And what makes things difficult for meta-heuristic are so-called plateaus, where you have several solutions or other solution with exactly the same best value. Then you don't know, and you have nothing to know whether you have to go left or right. So if you are not satisfied with this, with one of these solutions here, what you can do, you can change your neighborhood. And for instance, you can try for the traveling salesman problems to replace 3 edges by 3 other edges, because maybe you can find improved solution. And in fact, for the traveling salesman problem, this neighborhood is generally better if you have to find a solution to an instance that is asymmetrical, because here, in fact, if you look at the tour that you perform more or less clockwise, then you don't change the sense of in which you go to each of these 3 passes here that are connected differently. But okay, perhaps with 3 of neighborhoods, it's still not good enough. Then you can go to the 4 of, 5 of, and so on. But if you do that, then the size of the neighborhood will grow very fastly, and it will be not very smart to evaluate all the possible exchange, for instance. So maybe you may want to limit the size of the neighborhood, and this is the idea of a candidate list. So here, again, an illustration for the private statement problem. An idea is just to select only the potentially interesting edges. And you can do that for a Euclidean traveling salesman by first building a Delaunay triangulation and say, okay, I will keep only the edges that are on the Delaunay triangulation for building a solution. And here I have superimposed to this graph the optimal solution of these small instances that is indicated with the bold lines. And apparently, almost all the edges of the Delaunay triangulation belongs, all the edges of the optimum solution belongs to the Delaunay triangulation. Not always the case, but maybe that's a good way, in fact, to limit the neighborhood size. On the contrary, you may want to expand your neighborhood because perhaps your neighborhood is just making too small changes. And you can reapply the B search that we have seen just before for constructive methods, but applied to neighborhoods. So you have here starting solutions. This one, that's a partial solution, that's a complete solution. You evaluate all the neighbor of this solution, you pick up the p-best, and from this p-best neighbor, you compute the neighbor of the neighbor, and so on, up to a given level k. And then here you have evaluated a number of different complete solutions. You say, okay, perhaps this one was the best that I have encountered here. So I will decide to make this move here. And then you can try with your new current solution that will be this one. Or you may want to directly go to that one that will be the best, the next solution for the next step. For the traveling salesman problem, there is another way to extend the neighborhood. That is Lin-Kernighan neighborhood. It is based on the neighborhood, but it's made possible to perform several moves at a time. And the idea of ejection chain is as follows. You pick your initial solution and you eject an element from your solution. For the traveling salesman, you can eject an edge, the red one here. So what you obtain here is just a path. And then this path is transformed into what is called a reference structure, where in fact you add here a new edge. So from you add an edge, this edge here. So from the end of this path here, you add an edge, and you create something that is not a tour, that is not a path, that is in fact a cycle here and a path that is called sometimes stem and cycle here. And what is interesting from this reference structure is that if you continue the ejection chain, if you eject, for instance, this edge here, you will get a path, And if you connect both ends of this path, then you can transform this reference structure into a solution, to a tool. And hopefully, you may have a tool that is shorter than the initial one. And what you have done here is just to opt smooth. But if it is not the case, then you can transform this reference structure into another reference structure whose weight is still lower than the weight of the initial solution. And you can iterate the process, have a third reference structure. And if in this third reference structure, you eject this edge here, and you connect the two ends of the path, then you will get here a tool, a complete tool, that is shorter than the initial one. So you stop the exception chain, and you say, okay, my new current solution will be this one. And in fact, for the rolling stage-one problem, this neighborhood is very, very good and provide excellent solution. It's a bit complicated. I don't know how Lin and Kenigan has imagined that process, but it works really well. Okay. Maybe with this neighborhood structure, even with ejection chain, the solution that you get is not good enough. So what you can do? Then you can use a randomized method. And certainly one of the oldest randomized method was the simulated annealing. When you have material that you heat here at a certain point, it will be in some kind of viscous state. So the particle of your elements of material are disorganized here. And if you cool down sufficiently slowly this material, you will the elements, the atoms, or will organize in crystalline states. Why? Because this crystalline state is a state of minimal internal energy of your material. So people have tried to say, okay, if physics can optimize the internal energy of material, why not using this process, simulate this process for optimizing fitness function? So here, simulated annealing is a kind of randomized local search. You get as input an initial solution, you have a function f, that is the analogy to the internal energy that you want to minimize. You have a neighborhood structure that to simulate the move of your particles, and you have a number of parameters here. The initial temperature, the final temperature, that should be lower than the initial one, and cooling factor alpha, that's speed at which you will cool your system. Initially, the current temperature is the initial temperature. And while this temperature is larger than the end temperature, you just generate a neighbor at random among your neighborhoods here. So you pick neighbor solution S prime at random. And then you compute the difference in fitness of both of these solutions. That is called here delta. And if the difference of objective value of the neighbor solution minus current one is lower than 0, it means that you have improved your solution. So you will keep this solution, and the neighbor solution will be the current one for the next iteration. But if the neighbor solution is worse than the current one, you may also accept this solution, but with a probability that depends on the degradation of the solution. So you generate a random number u uniformly between 0 and 1. And if that's a magic formula for the simulated annealing, e to the power of minus delta over the current temperature is larger than u, then even if S prime is worse than S, you accept this solution. I should have written here S prime. And if you do that for traveling salesman problem, for instance, here is the evolution of with the iteration. Here is the evolution of the objective function. So at the beginning, I've provided a relatively good solution to the simulated annealing. And since at the beginning, the temperature is very high, I will start to, in fact, degrade the quality of the solution that I produce. And then, since at each iteration or periodically I lower the temperature, then I will improve, in fact, my solution, and eventually I can get solutions that are better than the starting one. And after a while, when the temperature is relatively low, then your system is frozen and nothing moves again. So here you are just performing iterations for doing nothing. But you can also add randomizing, not to modify a solution, but to build a solution. And that's the idea of really randomized adaptive procedure or RAST. And so, in fact, I put in red here what is different from pure greedy algorithm. You recognize here, in fact, a greedy algorithm in that part here. But what differs here is that you have an additional parameter. I've called it also alpha here because it's a name, but that has nothing to do with the cooling schedule we have seen before. This alpha is there for not choosing at each step the one that the element with the lowest incremental cost function, but you choose an element at random between the minimum value of the incremental cost function that you can have and this minimum value plus alpha times the maximum minus the minimum, so a little bit more than the minimum incremental cost function that we can have. And in fact, here, if you have alpha that is equals to 0, you have just a greedy algorithm, almost deterministic. And if you have alpha that is 1, you have just random building. And in between, you will get greedy randomized solution S here. This solution, you know that generally you have to improve it with a local search, so you can do that. So you improve the solution that you got with your greedy randomized step here with a local search. So you adapt this solution S. Then here you will retain this solution if it is the best that you have found. And since here now you are building random solution or solution with some randomness, if you can repeat this twice and get perhaps other solution. So you can repeat this until you are tired here for IMAX iteration. Now, one of the last steps is meta-heuristic learning principle. First, we can have construction learning. We can try to learn how to construct a solution. And the idea, in fact, or a simplified idea, is just to use this graph here and to add here somewhere some learning mechanism. So instead of using or adding the element that is between Cmin and Cmax here, you choose this element by computing here also statistics, so E for each element E that constitutes a partial solution. This statistic here is generally some kind of, let us say, running average that depends on the number of times we have observed this element E in the solutions that we have built, or it can depend on the values of the solution you have built, so the fitness of the solution. And I will present you the max-min and system, where you say, okay, I want to maintain these tau E in between two different bounds, tau min and tau max. So instead of choosing your element only looking at the incremental cost function, you choose it by mixing in some way these a priori interesting on putting E in your solution and the a posteriori interest of putting E in your solution with the a priori interest to putting E in your solution. There are other options that you can add naturally, or you can build several solutions in parallel. You can want to update these tau that are all in the vocabulary of artificial and system, the artificial pheromone with other kind of solution. And if we want to look at the max, min, and system frame, you see that it's becoming something quite complicated. But in fact, what is important here is just here, that line here, where in fact here you recognize kind of greedy algorithm, but it is randomized with another function here relative to grasp, and that's the typical ant colony formula, where you have to add two parameters, alpha and beta, to weighten the importance you give either to the a posteriori interest of including element E in your solution, or the a priori interest of this element. Then you apply the local search, like in GRASP, you store the best solution found, if it is the case. And here are the formula to update the statistics that you associate to each element. Now, in this max-min and system, you can build several solutions, M solutions in parallel. You can do that, even if you throw away n-1 just for updating this pheromone. And finally, you can repeat everything for IMAX iterations. That was for the solution building learning. You can also try to learn how to modify a solution. And the local search learning is typical taboo search idea. So, taboo search is a local search based on a local search with the best improvement policies that we have seen before. But it allows against degrading moves. But if you allow degrading moves, the problems that you may face is that you can visit cyclically the same subset of solution and get nothing else. So to avoid this, you have to forbid something. Perhaps you can forbid to come back to a solution that was already visited. So this solution is forbidden, so the solution is taboo, and that gives the name to the method proposed by Glover. And but also, if you don't want to store all the solutions that visited, you can have something simpler. You forbid to perform the reverse of a move that we have recently used. So here you have short-term memory. And you can add also long-term memory here. For instance, you can penalize moves that are frequently performed because you may want to go somewhere else in your neighborhood space or in your solution space. Or you may want to force to use moves that are never performed, or not performed for a long time. And these are long-term memory. And there are lots of other strategies that were proposed in the original work. In the context of taboo search, for instance, Glover spoke about these candidate lists that we have seen before, oscillation strategy, aspiration, so here is the simple taboo search frame. Here you have again an initial solution, a neighborhood structure, a fitness function that you want to minimize. And at minima, you have two parameters, the number of iterations you want to perform, and the length of your memory or the duration of your memory, D. So here you have the part where you are looking for the best neighbor of your current solution, but it is just a change here because among the neighbor solution, you ignore those that are marked as taboo, so those that are forbidden. If you find a neighbor. Hopefully, you should find a neighbor. Otherwise, it means that, in fact, your parameter D is too large and no moves are allowed. Then you perform this modification, even if it brings back you to a solution that is worse than the current one. And then you mark the previous current solution as taboo, or the reverse of the move from S to the neighbor solution as taboo. And this is taboo, let's say, for the iteration. That's the basic idea of taboo search. Finally, you can also try to learn with complete solutions. And that's the idea of population learning. On the top here, and in color, for those that are not Belgian, are 5 different solutions that I've got with not so good technique, but a very fast one that we can log n, and we'll see how to build this solution later. So these solutions are not so good, but if you make the union of all these solutions, you will get this graph here, and on which I have again superimposed the optimal solution of this Euclidean problem. And we see then that in as few as 5 different solutions, I've got almost all the edges of the optimal solution. So that's the idea of population learning. So you try to generate a number of different solutions, a population of solutions. And then from this population of solution, you select a number of individual here for reproduction about the parents. And then you can get what is called a new solution here that will eventually be inserted in your population. But what must be important in evolutionary algorithm is the management of the population here. And the principle of the population management should be as follows. You should keep a subset of good solutions in your population because you are interested by good solutions. So you have a subset of elite solutions in your population. But also in your population, you should also get different solutions. Solutions that are as scattered as possible. So that, in fact, when you use solution or several solutions, you can get new solution with completely different structure. And there are several ways to exploit the population. You can mix only 2 solutions, that the standard genetic crossover operator and computation operator. Or you can mix several solutions at a time. That's the idea of scatter search. Or you can apply the local search to the newly created solution. That's an idea of memetic algorithm. Or you can go from a starting solution to a target solution of your population using a neighborhood. This is the fast relinking strategy. Getting an offspring, okay, you can imagine there are technical ways to get an offspring. And it clearly depends on the problem, but it's technically possible. But what is important here is that if you start with a solution where all solutions are almost identical, you can imagine that the offering generated by these two solutions here will be almost the same as those as the parents here. And also for the dark one here or the one dot here. Maybe it would be more interesting to have this kind of population, various population where no point cross with several points, a dark with a red one, and so on. And with scatter search, you can also list several solutions at a time. Maybe there is still a technical solution for your problem. Apparently, beetles can do that also. Finally, the last strategy for exploiting population of solution is path relinking. So imagine here that in your population of solution, you have this solution here and this one. And you want to go from this solution to this target solution. Then what you can do here, you can look at all the neighbors of this starting solution that are closer to the target solution. So you evaluate all the neighbors that are of this solution that are closer to the target solution. Maybe the best neighbor relative to the fitness function is this one. So you go to that solution and you repeat the process. You compute the neighbor of these solutions that are closer to the target solution, and so on, until you get the target solution. And maybe on this path here, you will get solutions that are better than the starting or the target solution. And in fact, you can easily add this strategy, for instance, in GRASP. Here, this method, GRASP with path relinking, is relatively straightforward because it contains only 3 parameters. The alpha parameters of the GRASP for randomize for the randomization of when you create a new solution, and your patients, IMAX, so many times you want to repeat the process, and mu, that is the size of the population, the number of elements that you want to keep in the population. So first, you are just creating a population of new solutions that are all different here, and you can do that with a graph. Then you repeat for IMAX iteration. You generate a new solution as again with standard graph, and you pick solution S prime at random among your population. Then you can apply a path linking between S and S prime. So you identify the solution as second that is best along the path from S to S prime. And if S second is not already in your population, and if S second is strictly better than a solution of your population, then S second will replace one solution of your population. But since you want to keep your population as diverse as possible, then it will just replace the solution that is the most difference of P, but that is worse than S prime. So you are sure that your population will contain only the best solution, and that your population will be as diverse as possible, at least with this method. So last chapter, that are the decomposition methods. And again, I will illustrate this on provinces. Suppose that you get not so good tour here. That is the one that we see with these thin lines. Then maybe it's relatively easy to improve that tour like that. You pick up a city, and along your tour here, you pick the air next cities. Then you have a path that is not so good, and you can try to optimize this path independently from the remaining. Since you have only air cities in your path, maybe you can use an exact method. So you can have even a math heuristic here. Then, from the last city here, you can do the same thing here for the next air city, and so on. And in fact, you can have a first round here where you improve your solution. Then you can just restart by considering overlapping paths. And here I made it only twice, and I got finally this solution that is in bold here. In fact, at the second tour, I have only performed two of the moves, in fact. But okay, I have only examined air cities at a time, not all the cities of the problem at and that's the idea of the pop music frame. Suppose that you have an initial solution S that is composed of few disjoint parts. What we have seen before, a part is just a city, so you have n disjoint points, but in general, for other problems, a part can be defined differently. You have an improvement method and a single parameter here. What pop music do? In a set U, you put initially all the parts of your solution, so S1 to SQ. Then you repeat main loop while this set U contains at least one part. You select part, a seed part as G, that is belonging to U. And then you build a subproblem R that is composed of the A parts that are the closest from your seed part as G. Then you tentatively optimize this subproblem that I call R. Now, there are two possibilities. Either you were able to optimize something in R or not. So if you see that in the neighborhood of your seed par SG, you were not able to improve something, you just remove SG from U. Otherwise, it means that maybe you have found an improvement to your prior solution. So you update your solution, you remove the parts of you that are not belonging to your updated solution, and you insert in you all the parts that are composing your subproblem. And you repeat this until you have no parts in you. Maybe this can be illustrated better on a centroid clustering problem. The part here is not just one single element of your problem, but it's a whole cluster of that you have found in your problem. So this could be a seed part. And then you can select around this seed part the cluster that are the closer to the seed cluster, and then you can try to optimize this subproblem here. And if you are successful, then the cluster of this subproblem will change. So you remove all the cluster from you that were in you from this subproblem, and then you have new clusters that are all inserted in your use set. And then you can focus somewhere else in your problem. You can apply this also to the vehicle routing problem relatively easily. A part here can be just a vehicle tour, so you select here a vehicle tour, that is this blue one, and a few of tour that are closer to this seed tool, and then you can optimize these selected tools independently, so you just get a smaller vehicle routing problem. The technique was also applied to map labeling problem, where here I give a small instance where you have 4 elements that you have to label with their name, Verdun or Lausanne, and you can choose where you want to put the label for each element here. You have 4 possible way to label one point. And you can transform this map labeling. Naturally, if you choose to put Yverdon here, then you cannot put orb here or here because there is an overlap, and you don't want that. So you can transform this into a stable set problem by adding vertex for each possible position of the label. You connect all the label corresponding to one object in a click, and you connect also the incompatible labels by an arc. And then if you find the maximum stable set in this graph, then this will provide you a solution to your problem. You can apply the pop music to this problem here, and in fact, this method is embedded in ArcGIS now. Here you have a seed part or seed element that is number 0 here with the 4 possible position for its label, and in number 1 here, those that are immediately interacting with that can be in conflict with this one, and so on. So you can isolate here sub-problem or subsets of elements that you want to label differently. Here I just select 25 different labels that can be optimized completely independently from the green one here that are not modified. When you want to apply pop music, the main difficulty is, in fact, to find an appropriate initial solution. And here is a way for the traveling salesman to get an appropriate solution with a complexity that is not too large, and to the power of 1.6 empirically. The idea is as follows. You select a sample of cities, and you find a good tour on this sample of the cities. And this good tour is indicated here in green. Then you group all the cities into a number of clusters around the cities that you have used in your sample here. And then you can try to optimize these not here or two successive clusters at a time with, let us say, two hop neighborhood. And then you can re-optimize all the tours that you have obtained with pop music frame. And for instance, you consider all possible successive cities or 50 successive cities. And you can optimize this with Lincolnigan, for instance. And here are the solution quality we have obtained on various traveling salesman problems with toroidal distances. That's not Euclidean problem. So in yellow are the solution we've got with this method here, and on the horizontal axis are the size of the problem, and on the vertical axis are the percentage above the optimum solution value. And we see that for problem relatively large, 10 million of cities, we were able to get a solution a bit more than 5% above the optimum. This is to compare with another greedy algorithm, a very simple one that is a nearest neighbor algorithm, where the solution asymptotically tends to be 22%, about 22% above the optimum solution. But this method is in n squared. And here we have a method that is in R to the power 1.6 that takes time for 10 millions of cities. So we have tried to find a way to build a solution in linearitmic time, so in n log n. And that's what we have obtained here with these red dots here. So we have a method now in n log n that is able to build a solution that is appropriate for our pop music framework, because if we apply this pop music to this solution, we got solutions that are generally less than 10% above the optimum, even for problem whose size is pretty large, more than 2 billion of cities. How are we getting these appropriate initial solution? So we do more or less the same thing, but we have a recursive decomposition here. So we start by creating a tour on R cities, and then we are making the clusters. And if these clusters are small enough, then we optimize them directly with the Lincolnigan. And if they are too large, like this one, then this cluster can be decomposed recursively, and so on. And here is the empirical complexity we have observed. On the yellow ones is previous method, just getting the initial solution in with the complexity empirically in n to the power 1.6. And applying pop music, what is quite interesting here is that pop music behaves almost linearly. So you can optimize this subproblem or complete problem linearly with the size of the problem. And here is our fast constructive method, and applying a fast pop music where you just do here these two improvements here. You get this time, and here you see that in within a few hours you are able to get a relatively good solution to the curling salesman. What is interesting with that method here is that if you superimpose these a few solutions that you can get with that, then you will get almost all the interesting edges of traveling salesman problem. And now, in fact, this method is embedded in the LTH solver for those who have already worked with this solver. So I'm at the end of the talk. Perhaps I can propose some research perspective. I've shown you how you can use this idea of filtering the edges and getting good neighborhood, limiting the neighborhood size for the salesman problem. But can it be the case for other type of problems? That's not evident. Perhaps that's the opportunity to test quantum programming for optimizing the small subproblem, because no quantum computer has not so many qubits, so that they are not able to solve relatively large problem. But perhaps a drawback is that that's not the optimization of the subproblem that takes time. That is the most complete problem. That is for getting the an appropriate initial solution. And perhaps also why not trying something with quantum programming here, because we perhaps don't have to get a very good solution, but a solution that is globally good. And for application to other problems, what I know is that it's not so easy to transpose straightforward this music ID to the quadratic assignment problem. We tried, but it was not working for this problem. Perhaps we had wrong modeling for that. And so it's not perhaps not working for all instances, even for the traveling salesman problem. But for instance, with completely random data, I don't think that this method will work. More generally, for metaheuristic, I think that we have to study a bit more the contribution of all these parameters and these options that of the heuristic we can build with metaheuristic building blocks. And finally, perhaps a good research perspective is that to try to merge these, all this idea of machine learning with metaheuristic, because I think there is a lot of work to do there. Okay, I'm at the end of the talk, so if you have some questions, please. Yeah.
Maybe I will just somewhere. Can you explain the difference in pop music 50 and pop music 225? Maybe.
Okay. Yeah. Okay. 20 pop music 50 is for which here all the subpaths of length 50 are Lincolnian optimum.
Okay.
For 255, in fact, I just decompose the tour into subpaths of length 255. Okay, so I took this value of the arbitrary, and then I've made only 2 optimizations. Okay. So if you have n cities in your tour, I have made only 2 times n over 255 optimization, subpath optimization here. So I'm not sure that all the subpaths of length 225 are optimum, and what worries are not. Yeah.
Thank you for the opportunity. I just want to make sure in the slide number 7 that you said that we can modify the SP into shortest problem, and we also can solve shortest problem using Bellman-Ford algorithm. As I know, Bellman-Ford algorithm can produce a global optimum solution. Then, if we apply Bellman-Ford algorithm to solve the TSP solution, can we also produce a global optimum solution too for TSP? No,
not at all. Not at all.
Not at all.
No. What I would say is that, in fact, for building these building blocks of Metaheuristic, we generally use things that exist for a long time. So these local search ID exists for a long time. They work for simple problem, but not necessarily for our problems, that's sure. So Bellman-Ford will certainly not find the optimum solution to a troubling salesman problem.
Okay. But it is possible to find a better solution also with Bellman-Ford algorithm. Find better solution.
No, I don't think so, because so you have to design a neighborhood, and then if you change the neighborhood, then you can improve solution, but otherwise you are stuck in a local optimum.
Thank you. That's
in the path management strategy, what's the actual justification to looking at immediate neighbors instead of looking at the whole population?
So you are not looking at all the neighbor, but only the neighbor that brings you closer to the target solution.
Yes, but why the neighbors?
So you have to define a neighborhood. And so the idea is to go from a starting solution to a target solution. So you have to change something in your solution. So you must have a neighborhood. And then there are many ways from going from the starting solution to the target solution. So you have to choose one path. This path is used by enumerating the neighbor of your starting solution, and you have to pick one of the neighbor that gets you closer to the target solution. So why not choosing the best neighbor? Best participant. I don't know if I've.
I can't wrap my head around the justification of looking at the neighbors instead of like randomizing the search in the whole population. Like, is there an actual purpose?
Yeah. In fact, if you look at this process, you have at maximum n steps for going from here to here, and you have a very limited number of solutions that are enumerated here. Because if you have here 7 or 8, 7 elements here, you have 5,000 elements in your solution space here. But here we have examined only a few of them.
In slide 50, when you show your the quality of the solution for the Egyptian method, it seems like you're not this one. With your one level recursion, the gap improved with the size of the instance. Doesn't seem logical. Maybe because it's a percentage of accuracy and
No. That just due to the fact that you have in fact larger and larger problems or close to that. Okay, so the samples get a little bit larger, and these clusters here also get larger. Since you are applying two clusters here, then it improves the solution because you have a larger subproblem. That's why, in fact, you get better solutions. Imagine that here you have a problem of size 100. Then you pick only 10, let us say 10 cities at random. You make a tour, and then you make 10 clusters. And then you optimize 20 cities at a time, more or less. Okay? But if you have 10,000 problem, then you will pick 100 cities for the sample, and then you will optimize subpaths of length 200. Then you have more freedom to improve. That's why, in fact, you improve from here to here.
Okay, because your sub optimization is on larger.
Yeah. It's getting slightly larger. I mean, the book, there is an interesting problem. While choosing 10 to the power 0.56, you will get a solution.
I have maybe one question. You don't speak explicitly about exploration and interpretation.
I didn't have time to put everything in the slides. That's true. So, the idea with this strategic oscillation is that sometimes you have to go away from where you were, and sometimes you have to focus on what in a small region where you are. So this is also the case for the AND system when you want to exploit the information that you have with these two TOE information, or do something else. Yeah, but okay, I can put everything in there.
Any more questions? Thanks for contributing.
Yes.